Cool. All right. Nice. I have to keep an eye on this recording the entire time because it, for whatever reason, stops recording whenever it feels like it. All right, Laplace transform. The Laplace transform of a function, f of t, is given by the integral from 0 to infinity of f of t e to the negative st dt. You're not going to like them at first. You're going to hate them because there's like, what's the point? Why am I wasting my time with this? Why am I making these differential equations a little bit harder than they need to be? It seems like I liked doing the method of undetermined coefficients. Variation of parameters might have been a little tedious, but I got the hang of it. Wasn't that bad. So why are we introducing a new complicated way of doing these things? Once you do get the hang of Laplace transforms, you actually are going to enjoy them a little bit more than usual. So hold on, let me pull the document up that I need.
I gotta put it up online.
Yeah, it's recording to be put up online. Hopefully it doesn't stop recording because sometimes it just stops recording. And sure enough, I'm sure this is going to happen, but I'm going to keep an eye on the recording so it doesn't. All right, so you might be asked to find the Laplace transform of some basic functions from first principles, like a quiz or one of the first questions on a test or something. It might be something like, find the Laplace transform of 1. And in fact, you're going to memorize these. You're going to memorize a lot of these. You probably already know this one. Do you happen to know what the Laplace transform of 1 is? Nope. Well, it's fine. We're going to find it.
I don't remember most of them.
What's up?
I don't remember most of them.
Oh, that's fine. Well, after a week, you're going to have a lot of these down. So Laplace transform of 1 merely means we're going to take the integral from 0 to infinity of 1 e to the negative st. What's the integral of e to the negative st? Remember, you're going to need this rule: the integral of e to the at is e to the at over a. Anytime you integrate e to the at, you divide by the coefficient of t. So the integral of e to the negative st would be negative e to the negative st over s. And we're evaluating this from 0 to infinity. A little tricky because you're like, what the hell do I get when I plug in infinity for t? Remember, think of it this way. Here's e to the x. Looks like this. Now, as x goes far to the right, e to the x blows up to infinity. But as x goes far to the left, goes to 0. And that's what's happening here. When I plug in infinity in for t, let's for a moment pretend I can plug in infinity here, I have a very large negative number. For these purposes, we assume s is positive. So if s is positive, we have a negative number here. So we have negative infinity. This is going towards 0. So, and you can do it using the Calc 2 method if you want to, which is supposed to say limit as b approaches infinity of negative e to the negative bt, or s here, over s, minus what you get when you plug in 0. When you plug in 0, you get e to the negative 0, or just e to the 0 over s. But again, what is this going to come out to be? 0. Because as you send the exponent of e to a really large negative number, it goes to 0. Basically, this is decaying as close to 0 as possible, so it goes to 0. Cool? What is this guy? E to the 0 is 1, so we have negative e to the 0, or negative 1 over s, which is just 1 over s. The Laplace transform of 1 is 1 over s. Cool? Let's move some chairs here. I want to see if this is like even on camera. Okay, we're on camera. Cool. All right, now we're going to find the Laplace transform of something a little bit different. You want me to erase? Okay. How about Laplace transform of e to the 7t? Well, that means the integral from 0 to infinity of e to the 7t times e to the negative st dt. And we can combine these, right? We can combine e to the 17 and e to the negative st, so we get e to the 7 minus s times t from 0 to infinity dt. The integral of which would be e to the 7 minus st over 7 minus s. We evaluate from 0 to infinity. Okay. Multiply, so we plug in infinity for t again, but again, this is going to be, we take s to be sufficiently large so that 7 minus s would be a negative number. So that we get e to the, we get 0 for our first term, minus what we get when we plug in 0. 0 times everything up here. If we plug in 0 for t, we get negative 7 minus, wow, I can't talk today. 7 minus s times 0 is 0. E to the 0 is 1. So we get 1 over 7 minus s. And really, instead of saying negative 1 over 7 minus s, we decide to distribute this negative to the denominator to get 1 over s minus 7. So what kind of conclusion can you draw about the Laplace transform of e to the at?
It's 1 over s minus a.
1 over s minus a. Good. Because we saw that it was 7, we got 1 over s minus 7. So naturally, if we saw the Laplace transform of e to the at, we would get 1 over s minus a. Cool? All right, let's try. We're not going to do t to the n. Back in my study HA day, I derived the one for Laplace transform of t to the n. That takes a long time to do because we don't know what the power on n is, so we have to kind of do a general formula, and this is not going to be pretty. The reason this is not pretty is because you have to use, do you have any idea?
By parts.
Parts. Let's do the tabular method. I'm not going to spend too much time on it, but you do t to the n, e to the negative st, t to the n minus 1. You take derivatives down this line, right? N times n minus 1, right?
Is this one of the ones that has like a
Factorial in it?
factorial?
Yeah. Negative e to the negative st over s, dot, dot, dot down the line until you get down to n factorial. This is because if you take n derivatives of, if I take the 7th derivative of x to the 7th, I get 7 factorial. So if I take n derivatives of t to the n, I get n factorial. So this is, down this column, I've taken n derivatives. And down this column, I've integrated n times. So I'm going to get negative e to the negative s. We don't know if this is going to be negative or not. That is the problem with this, is that you have to do some sort of induction. We don't know if this is going to be a negative or not. Here's all you need to know, though, is that when you do this multiplication out, boop, 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 the only term that matters is this last one. Might be negative, might be positive, we have no idea. E to the negative st over s to the n plus 1. So this would be over s to the n. The first n minus 1 multiplications are going to be 0 when I plug in infinity. And they're also going to be 0 when I plug in 0. Here's why. All these terms contain that e to the negative st term, right? What happens when I plug in infinity for any of these? 0. For all these, it would get 0. But what happens when I plug in 0? Well, these terms won't go away when I plug in 0 for them. What happens when I plug in 0 to this, though? What's 0 to the n? 0, right? What's 0 to the n here? 0. All the terms up until n factorial will give me 0. So the only term that, long story short, here's what boils down. I get n factorial over s to the n plus 1. All the other terms drop out. All the other terms go away. And here's the interesting thing. The tabular method actually works out that it doesn't matter whether you got a negative here or not, because you remember you alternate the negative switching anyway. So, long story short, that's the result. Laplace transform of t to the n is n factorial over s to the n plus 1. I don't think you have to prove it, but if you do, make sure your professor would have gone over it at length and told you how to prove it. But this is typically not a test question. Your professor really has to be a dick if he wants you to prove this. Again, probably using some induction proof. Cool? So we've got a few tools. We're going to get a couple more about sine and cosine. Deriving these is also very difficult because you might remember from Calc 2 doing an integral like this, e to the 2t sine of 5t. This was Calc 2. You remember doing this integral? You had to do parts for this, but it was called a circular integral. That when you did the parts integral, you got it just
came back.
Yeah, it came back again, right? You had some e to the 2t cosine 5t term, whatever, with some constant like 2 or something. And then you had minus integral of e to the 2t cosine 5t, and again over some constant like 2. Again, I'm making up these constants, but then you say, okay, well, now I have this again, right? Don't even bother writing this down. It's not worth your time. You're like, oh, great. Now what? I do the same thing again. But then e to the 2t sine 5t showed up again, and you took this term from the right and threw it over to the left and divided by the constant. That's what you ended up doing. So proving the Laplace transform of sine, or we'll say sine of bt, is kind of a pain in the ass, because doing that integral from 0 to infinity of sine of bt times e to the negative st, from 0 to infinity, I did say that, would be using this circular method to do that. And again, Wolfram Alpha can help you if you need to show that some integral like that, but it's best to just say it's probably not going to happen. Let's hope. Let's cross our fingers. So Laplace transform of this guy is just b, whatever constant that is, over s squared plus b squared. And cosine is very similar.
It's S.
Right, it's s. So it's the variable s over s squared plus b squared. So keep that in mind. B is a constant. And s is a variable. Cool? Alright, now with that in mind, we can construct very long Laplace transforms, such as something like this. What's the Laplace transform of 3 plus 4e to the 5t plus cosine of 3t, let's say 2 cosine 3t, minus t to the 4th. What is this Laplace transform? Let's start with the 3. What's the Laplace transform of 3?
1 over S.
Well, we know the Laplace transform of 1 is 1 over s. The Laplace transform of 3 is what? 3 over s. Good. What's the Laplace transform of e to the 5t? We know the Laplace transform of e to the at is 1 over s minus a, so the Laplace transform of e to the 5t is 1 over s minus 5. I'm not quite out of the woods there because I still have a 4 there. But the 1 over s minus 5 takes care of the e to the 5t, but that's okay because the 4 just does this. Put a 4. Yeah. A lot of people think, does something different have to happen with this 4? No, you just carry it over like it's a derivative or an integral. Just bring it through. Laplace transform of 2 cosine 3t. We know that cosine 3t produces s over s squared plus 9, because that's b squared. And we have the 2 there, so we're going to carry the 2 through. So it's not 25, it's a 2s. A lot of people don't like how my s's look like my 5s. Yeah, see? S minus s is 0, it's just being defined. And then lastly, t to the 4th. What's the Laplace transform of t to the 4th? That would be 4 factorial, which is 24. You can say 4 factorial, because that was a 4, over s to the 5th. So this is one giant Laplace transform. This is a good fair game question on a test, because it's testing you on knowing 4 different Laplace transforms and making sure you know your table. You have a question?
No.
Okay. There's some other interesting properties. And this is one you're going to want to write down. Laplace transform of e to the at times any function f of t is the same as, okay, let's say, suppose the Laplace transform of f of t, we often will call this capital F of s. So it's a different function and by a different variable, s. Okay? If the Laplace transform of f of t is f of s, then the Laplace transform of e to the at times f of t is the same damn thing, except shifted by a. Let's look at an example. What would the Laplace transform of e to the 4t cosine of 5t be? Start by asking yourself, what's the Laplace transform of just cosine 5t? What is the Laplace transform of cosine 5t?
S.
S.
Over S.
Let's not use 5 because my 5 look like s's, right? So cosine of 7t would be s over s squared plus what?
49.
49. 7 squared is 49. But because this is being multiplied by an s to the 4, an e to the 4t, every instance of s gets shifted by 4 units. Cool? Let's try another one. What's the Laplace transform of e to the 2t times t cubed? Well, that would be, so start by saying what's the Laplace transform of t cubed? We know that to be 3 factorial, or 6, over s to the 4. 3 factorial, and you take the power on t, add 1 to it, and get to your denominator s term. But it's e to the 2t, so every instance of s gets shifted to the right by 2 units. So I'm going to have, instead of s to the 4th, I have s minus 2 to the 4th. Good? So this is this is a really, I don't know why I'm laughing. This is a really important rule to know, because you might be looking at this, might look daunting, but just know I shift everything by 4. Cool. Let's do another trick that you need to know.
Can you do like inverse Laplace?
Yeah, we'll get there in a minute. Gotta start with all the forward direction stuff before we start. Like, what did you have to learn about everything before you talk about integration? Like, what did you spend the first several months learning about before you talk about integration?
Derivatives.
Yeah. So I have to talk about everything derivatives first before I talk about integration, right? I can say, so the derivative of x squared, that's 2x. Now, all right, we're done. Let's go on and talk about the integral of cosine of x. Anyone? Anyone? That wouldn't be fair. So I have to finish up what I want to say about moving forward before we start talking about inverse Laplace transform. So this last rule is find the Laplace transform of f of t again. We call that, you don't have to rewrite this, but just say same rules apply. That is the Laplace transform of some function f of t is capital F of s. Then the Laplace transform of t to the n times that function. So this rule kind of sucks. Is -1 to the n times let's say let's kind of talk about what this says briefly. It says that if I have t to the n being multiplied by a function, I have to take some number of whatever power of t I have here, take that many derivatives of the original functions attached to, or the Laplace of the original function it's attached to, and multiply by -1 to the n for as many. I'm gonna stop and start just so I don't lose everything, because that's why I'm back. Okay. We're gonna put this to practice now, so we can see what the hell this is all about. Here's an example. Although this is a trick example. That's nice of me. It's a tricky example because I'm almost suggesting that you should use this. But this is a pain in the ass. This is a huge pain in the ass. Besides, look at the t to the 5th would suggest how many derivatives that we need to take. 5 derivatives. We're not doing that. There's no way we're doing that. What we can do? Here's what we can do instead. This is a t to the 5, right? But attached to it is an e to the 6t, which means that we just take the Laplace transform of t to the 5 and do what?
Multiply.
Nope. What does the e to the 6t mean we need to do?
Oh, subtract.
We're not going to subtract. This is, what am I doing here? Yeah, we're subtracting. I want you to use a particular word. It starts with s, not subtract. Shh.
Oh, shift?
Yes, shift. So t to the 5th, Laplace transform of t to the 5th is 5 factorial over s to the 6, right? But because we have an e to the 6t here, this means we're going to replace this s by s minus 6. Does that make sense? And notice I don't need to use this rule up here, this upper left rule, which is good because I wasn't all about taking 5 derivatives of e to the 6t. Cool? Keep that in mind. That's a way that they'll try and trick you. But now we're going to encounter one where we actually have to use this rule. Okay? We start by asking ourselves, what's the Laplace transform of sine of 3t? Laplace transform of sine of 3t is equal to what? 3 over s squared plus 9, right? Well, because we have t sine 3t here, what do I have to do? I need a -1 to the 1, so I'm going to put a negative in there. I'll also put a negative in there now. Yeah, don't forget we're going to do that negative. And then what do I need to do? I put n is 1, so I need to take one derivative of this Laplace transform. For differentiation purposes, I'm going to write this as 3 times s squared plus 9 to the -1, so that when I apply the power rule, -1 will come down in front. I hope the recording stopped for a second. -3 times s squared plus 9 now to the -2 times the derivative of the inside function, which is 2s. So we get -6s over s squared plus 9 squared. So this is the derivative of the Laplace transform of sine of 3t, which is going to go here. Don't forget, though, that it's negative, negative, so it becomes a positive. We have a negative, negative success, so it becomes positive. And that's the Laplace transform of t sine 3t. Cool? Now, I could have made this a little more nightmarish, especially if I had something like this. T to the 2. That would mean 2 derivatives of this guy. So I take one more derivative, but that would require what? Quotient rule. I'm not about that last sheet, remember? Because that means you have to take another derivative, right? Because if you have a power of t squared, I have to take 2 derivatives to get this Laplace transform. We could do one more. Let's do one more briefly. Or at least talk about what we would do. The Laplace transform of t e to the 2t cosine of 3t. Now you could say, this e to the 2t is going to cause a shift. That helps you get rid of this e to the 2t. But then I'd ask you, what's the Laplace transform of t cosine 3t? Do you know? It's not one of the ones you know. You know Laplace transform of t to the n. You know Laplace transform of e to the t. You know Laplace transform of 1. You know Laplace transform of cosine and sine. But you don't know Laplace transform of t cosine. The only way you could ever get this is using this rule here. So what we're going to do first is say, do we know this guy's Laplace transform? Yes, we do, because we know this one, and we can do a shift. So what's the Laplace transform of cosine 3t?
S over s squared plus 9.
S over s squared plus 9. But because of this e to the 2t, I can shift every instance of s by 2.
S minus 2.
Excellent. So then how would I get the Laplace transform of t e to the 2t cosine 3t? What would that mean I need to do? Now that I have this, differentiate this, differentiate this, and multiply by a negative 1 to the 1, right? This would require a quotient rule, but I might expand.
Wait, would it be negative 1 to the 2?
No, how many?
Oh, wait, no, never mind.
I only have one
I'm
thing,
looking at
right?
the E.
Yeah, look at here, yeah, plus 13. And then do quotient rule on this. That'd be low d high minus high d low over low squared, and then multiply by a factor of negative 1 because of this term there. Cool? Again, not exactly the best, not exactly the fun thing to do because quotient rule sucks. I think we can agree quotient rule can fuck off. Alright. Now we'll talk about inverse because I think we've kind of covered everything as far as moving forward from a function of a Laplace transform or Laplace transform of a function. Now we're going to talk about, given a Laplace transform, how can we find the function it started from? And really, I actually haven't figured out a good method for this. To kind of play it by ear. Look at some. Give me a sec. Okay. Compute the Laplace inverse of something like 120 over s to the 6th. What's the Laplace inverse of that? Well, since the numbers are nice, and we happen to know that 120 is what? 5
Times.
4 times 3 times 2 times 1, namely that it's 5 what?
Factorial.
120 is 5 factorial. I did this deliberately. That's nice. That's not what was going to happen, though. So whose Laplace transform is 5 factorial over s to the 6th?
T to the 5.
T to the 5th, right? Now, what if I gave you something like this? Laplace inverse of 12 over, let's not use 12, let's use 6. 6 over s to the 5th. This is kind of weird. And again, I haven't figured out a good way to tackle this one. I can kind of give you some suggestions. We'll kind of do a what would Andrew do method. Like, look at your bracelet, WWAD. What would Andrew do? I recognize that s to the 5th would have come from a Laplace transform of t to the 4th. We know Laplace transform of t to the 4th is 24 over s to the 5th, right? We don't have 24 over s to the 5th, right? That's okay. I'm going to factor out this 6. Okay, so there'd be a 1 here now, I guess. And I want 24 over s to the 5th. So here's what I'm going to do. I see a 1 over s to the 5th. I'm going to put a 24 there. But I can't just put 24 on the inside without putting what on the outside? 24 where? Where did I put the 24 in here?
On the bottom.
On the top, so I need to put 1 on the bottom. Does that make sense? So 6 over 24, really that boils down to 1/4. But now I have 1/4 Laplace inverse of 24 over s to the 5th. What's the Laplace inverse of 24 over s to the 5th? We said t to the 4th, right? So we have 1/4 t to the 4th. Okay? Let's try something a bit harder. I wonder how these markers are. These are pretty good. Let's see. All right. I'm going to stop and start. What do you think? Any ideas?
Our professor usually does like partial fraction.
No, that's not going to work here. Partial fraction ain't going to play. Because after all, there's only one denominator. This is only a linear term. We'll get into some crazier ones though. Yeah, for sure. Those are going to be fun.
Look for the shift.
There's only a shift. What kind of shift?
4.
4. So we're going to have an e to the 4 t. Wow, this is showing up in the video. Not really. Not enough. Oh, red. Kinda. Yeah, a little bit better. Okay, e to the 4t. Definitely we have an e to the 4t. What else do we have? That, taking into account the shift, now I have just s to the 4th. That would have come from a what?
T.
Mm-hmm.
A t to the 4th?
Yeah, nope.
Wait, a t to the 3, right?
T to the 3rd, right? So that'd be a t to the 3rd. The power on the s down the bottom is 4, so the power on t from the original is 1 less, namely t cubed. Cool? This isn't quite right though. Why? What's the Laplace transform of t cubed?
1.
So this is the rule we're using. Laplace transform of t to the n is n factorial over s to the n plus 1. So what's the Laplace transform of t cubed?
3 factorial.
3 factorial over s to the 4th, right?
Mm-hmm.
Here we have 18 over s to the 4th. Basically, what is 3 factorial?
27. 21.
Neither. None of those. 4 factorial is 24. 3 factorial is not 9.
Wait, no, 9 times 3.
Nope.
Oh wait, it's 1 times 2 times 3.
Yes. Still more factorials. Yeah, okay, it's in the video. Good. And 5 factorial, just for good measure, is 120. It's just worth memorizing, just like you know, what's 12 squared? What's 12 squared?
140.
You just know that, right? It's good to just know these factorials. All right. What was I going to say now? Okay, where are we? We know there's a shift of 4, so that's why we have e to the 4t. We know there's an s to the 4th down below, which meant the original t power must have been 3, because we know that we bump power up this guy by 1, right?
So 3 times 3 factorial?
Yeah, exactly. So up here, yeah, exactly, you're working backwards, right? We know that the Laplace transform of t cubed would be, what? 6 over s to the 4. We already have an 18, right? So already, the 18 has got the 6 inside of it, right?
Yeah.
So what's left over after I factor out a 6 from the 18? A 3. So I need a 3 here. Make sense? And again, that's kind of just like tinkering with it. That's not actually a good method, right? It's just kind of tinkering and saying, hey, look, or you could say this. You could kind of always do this. You could say, what do I want to be here so this works? I know that I want the 6 to be, I'm going to factor out the 18. Great, this red marker sucks. I'm going to factor out the 18, and I have a 1. I want a 6 to be there, so I'm going to put a 6 there.
And divide by 6.
But because I have a 6 here, right, because I put a 6 in the numerator, I have to put a 6 out here, and there's your 3 is going to come out. There's a better method. My method's more tinkering than factoring something out and dividing because I think it's silly, but hey, it works every time. I factor out the number I have here, put the number I need here. I realize that because this is a t cube, I need a 6 here, a 3 factorial, and then put a 1 6 out in front. That will always work. Cool? So the Laplace inverse of this guy is 3 e to the 4t t cubed. Cool? All right, let's do one more. Let's do 2 more. Laplace inverse of 8 over s minus 3 squared plus 25. I wish I had a microphone too, because I know that whenever people watch this video, you just hear an echo, a reverb. Are you looking for a microphone?
Yeah.
No, I don't think there's one. I wonder if I could hook one up. I'd probably hook one up through my sound port, like one of the ones, like the Mac mics. Anyway, what are we dealing with here? What's your first instinct? What kind of function? Not a cosine, because a cosine will have an s in the top, so this is a sine. All right? Sine of what?
Phi.
Uh-huh. Right? What else? What else is involved?
A shift.
And how much?
3.
3, so I should have a what out here?
T.
E to the 3t. Right? Not t to anything. A shift is caused by that exponential term. Good? So, the only problem is, what's the Laplace transform of sine of 5t?
5 over.
5 over s squared plus 25, right? But what do we have here?
8.
Right, but we'll do what we usually do. Pull out the 8. What do we want here?
5.
A 5. Right? But if we put a 5 here, means what do we have at the bottom?
Divide.
Right. So this makes sense. This is, we have the 5 over s squared plus 25, that's the sine of 5t, and we have a shift of 3 units that gives the e to the 3t. So this part's all taken care of. But we still have an 8/5 up front, so we're going to put 8/5. Make sense? Do one more, like this. Laplace inverse of 3s over s minus 1 squared plus 1 plus 2 over s minus 4 squared plus 9. So what do we have here?
Cosine and sine.
We have a cosine and a sine. This is a cosine. Notice that the nice thing about cosine is that you don't really have to tweak with this numerator. The cosine always has a what here? S. This constant just comes out. So it's going to be 3 cosine of what? 1t, or just t, right? And what do we have here?
E to the 1.
E to the 1. We have an e to the t shift. That's it. That's pretty easy, right? There's a cosine in here. I don't have to dig around with that 3. That 3 can just come right out. There's a shift of 1, so I need an e to the t, and the power, or this is 1 squared, so the coefficient of t on the inside of the cosine is 1. I do have to toy around with the numerator up here. It's going to mess me up a little bit, but we'll deal with it. First off, we have what kind of shift?
4.
4 to the right, so e to the 4t. This is a sine, right? So it's going to be sine of what?
3t.
3t. Now again, typically, with sine, what's our numerator going to be? Sine of 3t, I should say. Sine of 3t, our numerator should be what?
3.
3. So we're going to take a 2 out. I guess technically I should put it here. We'll take a 2 out. But I'm going to put a 3 up top. I can't put a 3 up top, though, just willy-nilly, unless I do what?
Divide.
Divide by 3 out here. There's your answer.
Question.
Yeah.
When you did s minus 4, it's to the 2. Never mind.
Cool.
Got it.
All right. Good. Now we're going to talk about, I guess you said something about professor doing partial fraction decomposition. Definitely, it's going to happen a lot. In fact, you do need to brush up on your partial fraction decomposition for this class. If you haven't done partial fractions in a while, it might be a little difficult for you. But we're going to do some practice just by virtue of doing these problems right now. So, the Laplace inverse of s plus 2 over s squared plus 3s minus 10. All right. First things first is to check to see if that denominator can be factored. Sure enough, s squared plus 3s minus 10 sure enough can be factored into s plus 5 times s minus 2. Okay? Now, we know that using partial fractions, we can break this into Laplace inverse of a over s plus 5 plus b over s minus 2. The values of a and b are to be determined by whatever method you like to use. You can use solving a system. We can also use that method called the cover-up method, which works pretty well in this case. Not always will that cover-up method work, so keep that in mind, that the cover-up method just might fail, or you might be able to get a couple values of a or b, but not all of them, and then you have to resort to solving a system of equations. So keep that in mind. We don't have to hear them. What value of s causes this denominator to be 0? Negative 5. So we're going to go plug negative 5 into this guy. What's negative 5 plus 2? Say again?
Negative 5 plus 2,
Mm-hmm.
negative 3.
Negative 3. Negative 5 minus 2?
Negative 7.
Negative 7. So we have negative 3 over negative 7, which is positive 3/7. So this is 3/7 here. What value of s causes this denominator to be 0?
2.
2. So we're going to plug 2 into, we're going to cover up the s minus 2 and plug in 2. 2 plus 2 is?
4.
2 plus 5 is?
7.
So we have 4 over 7. Our value of b is 4/7. Now it's a piece of cake from here. What's the Laplace inverse, or whose Laplace transform is 1 over s plus 5? How much of this is the shift by?
5.
5, but it's to the left this time, so the Laplace inverse of this would be 3/7 e to the negative 5t. And the Laplace inverse of this 4/7 over s minus 2 would be plus 4/7 e to the 2t. Cool?
Okay.
Let's do another.
So if it's the opposite sign, you just put that in the...
Yeah, there's a plus 5, now it's a minus 5, right? Alright, this is going to be a pain. Alright, so we have a repeated linear factor here. We have s minus 1 squared. With that in mind, this is going to break up into a over s minus 1 plus b over s minus 1 squared. Is that familiar? That for every time you have a repeated linear factor, you have to do it twice, or up until the highest power. So if we had s minus 1 to the 4th, we need a c over s minus 1 cubed and a d over s minus 1 to the 4th. Fortunately, we only have just 2. Now remember, the cover-up method can only tackle
2.
One of these, and it tackles this guy. Which one of these 2 does the cover-up method tackle? Nope, one on the right. It always tackles the highest power one. So keep that in mind. Cover-up method always deals with the highest power linear term. Ready? So what value of s causes this denominator to be 0? 1. So we're going to plug in 1 after we cover this up. 1 plus 2 is 3, minus 1 is 2. 1 plus 2 is 3, so we have 2 over 3, which is 2/3. What value of s causes this to be 0? Negative 2. So we have negative 2 squared is 4. Negative 2 times 2 is negative 4, so we have 4 minus 4 is 0. Minus 1 is negative 1. Negative 2 minus 1 is negative 3 squared is 9, so we have negative 1 over 9. Negative 1/9. You can tell I didn't pick these numbers ahead of time because we're getting these ugly fractions, but hey, that sometimes will happen. Okay. We can't find the value of a using the cover method. So we're going to have to use some sort of getting a common denominator, sadly. So what does this term need that those terms have? And as far as the denominator goes. This s minus 1 needs what?
Squared.
It needs an extra factor of s minus 1. What else does it need?
Plus 3.
And s plus 2. Right? This a term needs an extra factor of s minus 1 and an extra factor of s plus 2. What does this term need?
S minus 1 and s.
It already has an s minus 1.
S plus 2.
It just needs an s plus 2. So this 2/3 just needs an s plus 2. And what does this fraction over here need?
S minus 2 squared.
S minus 1 squared.
That's
Okay. Minus 1/9 times S minus 1 squared. Good. And this result is supposed to be, let's see if I'm still on camera. I am, but I'm going to stop and start so I don't lose anything. We are going to, what do we need? We need the numerator of S squared plus 2S minus 1. Alright, let's multiply a lot of this stuff out. We get AS squared. Here's what I'm going to do. Watch this. Really, how many variables do I need? How many variables am I looking for? I found B and I found C, didn't I? So I'm looking for just one. I'm going to skip the bullshit S term. I'm going to skip the bullshit constant term. We got an AS squared. Any S squared terms over here? Any S squared terms over here? Yes. How many S squareds?
2. 1. Well, 1/9.
What should I write?
1/9.
Not 1/9. Minus 1/9.
Oh.
Yes. I need you to say the minus. And how many S squareds do I have on the right?
1.
Just S squared, right? Or you could say, what I used to do is say my S squared terms. How many S squared terms do I have here? I have A. How many S squared terms do I have here? Minus 1/9. How many S squareds do I have? 1. All right, I have 1. Good. Add 1/9 to the right hand side, and you get A equals 10/9. So we found A equals 10/9. All right. Now, and again, I didn't have to multiply this whole thing out. I had to multiply this. In fact, I didn't even look at this guy. There was no term in here that contained an S squared, so I didn't even bother. I was allowed to skip it. So make your life easier because you're going to be solving a lot of these partial fraction decomposition equations throughout the rest of for the next month-ish. So that's going to be, I guess, not maybe not the next month because what? About a month left to class-ish. Anyway, make your life easier. Don't write out too much more than you have to. And in this case, I only had to examine the S squared terms, so that was cool. All right. Now let's start with the Laplace inverse. 10/9 over S minus 1. What is the S minus 1 going to give you? What's the Laplace inverse of 1 over S minus 9?
E to the 1t.
Right. This is e to the 1t, or just e to the t. But we have a 10/9 as a coefficient. How about this 2/3 over S minus 1 squared? Ooh, tougher. Let's skip it for now. We're going to come to this guy, and we'll talk about how to deal with this guy in a minute. Negative 1/9 over S plus 2, we know it would be what?
Negative 1/9 e to the negative 2t.
Perfect, e to the negative 2t. Good. Now this guy, we have an S minus 1 squared. How would we ever have produced an S squared?
T.
A t, right? There's going to be some sort of t involved. So the Laplace transform of t is 1 over t squared. Okay? So this must have been some sort of t. Let's say plus 2/3 t. Right? But the Laplace transform of 2/3 t would have been 2/3 over t squared. But this is, 2/3 over s squared. Shit. S squared. Cool. Let's not make that mistake. Laplace transform of t, 1 over s squared. So the Laplace transform of 2/3 t would be 2/3 times 1 over s squared. Well, we have s minus 1 squared. So what must have caused that? E to the t, right? Some shift. There's your answer. Okay. Let's do something harder. This is a good one. So I'm gonna puncture your bubble here. The denominator does not factor. So we're probably gonna want to complete the square. And in general, when the denominator doesn't factor, it's usually indicative of a sine or a cosine. So we're gonna complete the square and call this s plus 2 over. How do you complete the square? What should I write? S goes here, squared. What goes here? Plus what?
3.
Plus 3. Good. Plus 3 squared.
9.
We're going to subtract it from the 13. If it's, for those of you wondering, I thought we added it. It's usually you add it to the other side of the equation, but there's no other side of the equation here, so you have to subtract it from the same side of the equation. So since we're on the same side, there's no equation. There's no other side to add it to. We're going to subtract it from this side. So we're subtracting the 3 squared is 9, subtract that from the 13 to get plus 4. Now this looks a little bit familiar, right? This is, looks like it's some sort of cosine or sine, right? Maybe both. We would love to do cosine, except for the fact that the shift here doesn't match, right? What is this? This is s plus 2. This is s plus 3. The shift is one or the other. It can't possibly be both. So here's what we're going to do. We can tweak that numerator just a little bit. Here's what we're going to do. Actually, you have any ideas?
Minus 2.
Not minus 2. This needs to match this, and it currently doesn't.
Add 1.
We're going to add 1. Subtract 1. Okay? So this is now the plus inverse of s plus 3 over s plus 3 squared plus 4 minus, or you say plus, what do you want to say here? Minus 1 over s plus 3 squared plus 4. Now that I've given the numerator of that first term the one that matches the inside of the parentheses, I can now take the inverse of it using that cosine rule. So this is what? Have a glance. It's got a shift of how much?
E to the 3.
Negative 3t. Is it a sine or a cosine?
Cosine.
It's a cosine. And what's our coefficient of t? 2t. Good. How about this guy? This is again another one with a shift. It's a sine, right? It's a sine of what?
E to the negative 3t. Sine of 2t.
Sine of 2t, good. But the problem is, you're on the right track. The problem with this is the Laplace transform of sine of 2t would have produced a what up here?
A 2.
A 2, but it didn't. So it must be up in front here.
1/2.
1/2. Does that make sense? I'm going to repeat that for those of you watching at home. This is a sine of 3t roughly, but the sine of 2t would have produced a 2 in the numerator, and it didn't. Meaning there must be a 1/2 in front, causing that 1/2 times a 2 to go away and become a 1. Cool? That's your Laplace inverse. Let's do another one like this. This is a good one to do. Let's do Laplace inverse of. Alright. 2s minus 5 over, let's make it really difficult, 2s squared plus 8s. Wait a second. This is kind of dickish. Really difficult. Again, that denominator doesn't factor, so sorry about that. But the denominator does factor in that I can pull off a what? 2. So let's do right off the bat, let's just do that, because I don't like that 2 sitting down there. Laplace inverse of 2s minus 5 over, this will become s squared plus 4s plus 29. Okay? Let's do minus 8s. Let's do minus 4s here. So, I changed that plus 8s to a minus 8s, and therefore it becomes a minus 4s. So s squared minus 4s plus 29. Again, doesn't factor, but I can complete the square. So I can have s minus 2 squared. Again, I say s minus 2 because 2 is half the coefficient of this 4. What's 2 squared? Sorry, I'll let you catch up. S squared minus 4s becomes s minus 2 squared. But I square that value of 2 there. What's 2 squared? 4. Peel it off the 29 to get what?
25.
Mm-hmm. Good? Once again, this inside of this parentheses does not match this numerator. And we want that to happen. Now, realistically, it would never happen because this is a 2s and that's an s. And I can't add s's, just subtract s's. So what I'm going to do is I'm going to factor out an s from the numerator. Or factor out an s, but factor out a 2. So I'm going to factor out a 2. I have 2 over 2, which is just 1, right? So let's write that. S minus 5 halves over s minus 2 squared plus 25. So we're almost there. We're almost out of the woods. This is s minus 5 halves. We want this to be what?
S minus 2.
So really, we almost have that. We have s minus 5 halves. What is 5 halves? Or how can I rewrite s minus 5 halves? As what? A lot of people think I need to do some sort of +1 -1 trick here or something like that. I don't need to. Here's why. If I had an s plus 2 squared, blah, 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 plus 1, and I had s plus 3 in the numerator, what could I do? I can just call this what? What is this?
S plus 2.
So what is this?
S plus 3.
Well, say it in terms of s plus 2.
Oh, s plus 2 plus 1.
Right. So what is this? Well, what do I have here? S minus 2. What is this?
S minus 2.5.
Minus 2.5, or s minus 2.
Minus 0.5.
Right. So we're going to say, by the way, I factor, so don't forget, I factor a 1/2 out from the beginning. I factor another 2 out from the numerator, so I had 1 here now.
So you're going to subtract 1/2 from the top, right?
Essentially, I'm not doing any plus or minus. I'm not really changing. I'm not doing that +1 minus trick that I did over here.
Okay.
It's just saying, what do I need? S minus 2. I already have S minus 2. It's just right here, but it's just too much. So I'm going to say Laplace inverse. Yeah, I'm going to be subtracting 1/2 in a way.
But not outside.
Right, not on the outside. I'm not doing any sort of plus minus trick. S minus 5/2 is S minus 2 minus 1/2. I think we can all agree to that, right? S minus 5/2 is S minus 2 minus an extra 1/2. We actually had more than we needed. So we take the S minus 2 that we need, we take the 2 that we need, pick that out, put it here, and said, oh, we'll get some leftover 1/2, we'll put that over here. We have S minus 2 over S minus 2 squared plus 25 minus 1/2 over S minus 2 squared plus 25. We're taking the Laplace inverse of this. Cool? I really didn't want this to happen because I wanted a coefficient of cosine to pop out, but it didn't because like, the 1/2 canceled with the 2, so whatever. Anyway, this is a cosine, right? Cosine of, or yeah.
To the 2t.
E to the 2t, we have a shift of 2.
Plus cosine 5t.
Cosine of 5t, exactly. And over here, this is going to be another e to the 2t. Let's put a minus here. Sine of 5t. However, if it was sine of 5t, when we took the Laplace transform, what would it have produced?
5.
A 5. What do we have up top?
1/2.
What do you multiply 5 by to get 1/2? 5 times what is 1/2? Solve for x.
Wouldn't you just do 5 over... Oh, never mind.
What should be here?
5.
But what is here?
No.
What did I multiply? What must have been multiplied by 5 to get 1/2?
1/10.
1/10. I like doing it that way. You don't have to. If you want to, you can do the whole... Let's do this thing. Pull the 1/2 out. Put a 5 here. We're putting a 5 here. It's a 5 on the bottom. 1/2 divided by 5 is 1/10. I think it's just cooler to do this. What do I see here? I see 1/2. What should be there? A 5. What do I multiply 5 by to get 1/2? A 1/10. So it must have been a 1/10 there. And that avoids this whole, I'm going to pull out the 1/2. I'm going to pull out put a 5 there. Of course, for some of you watching at home, or anyone in the room, that's probably what you need to do to get your bearings straight to start. But watch me. This is the Jedi mind trick. This is like pretty cool. 1/10, 1/2 is here. I know it's supposed to be a 5. What do I multiply 5 by to get 1/2? 1/10. Boom. Done. I don't have to pull anything out. Cool. All right. We're done with Laplace inverse, at least some of the more complicated ones. And then new stuff, I guess. Let me see what I had written down. Do you have any questions?
No.
That's probably where you stopped in class most recently.
We did like initial value problems.
Ooh, solving them?
Yeah.
Oh, okay. No, we
We
did that.
started to, but that was about it.
Okay, we can talk about that. Solve the initial value problem. We got an example.
He did an ln one, but it's like the same thing. You just split it. He did that.
Oh yeah, this one's difficult though.
But I feel like he wouldn't give us something.
Yeah, he would. We have to talk about that in a minute. We're gonna solve some initial value problems though. Let's do 4. And then y of 0 equals 2, y prime is 2, y prime is 0 equals 12. Okay. Some other rules we need to know, we didn't really quite talk about, but there's just two more. It's how to take the Laplace transform of y prime and y double prime. So when we do these problems, when we solve these differential equations using Laplace transform, here's what we're going to do. We're going to call the Laplace transform of y of t, or just y, we're going to call it what? Capital Y of s. Okay? The Laplace transform of y prime of t would be sy of s minus the value of the function at 0, minus the value of little y, 0. And then Laplace transform of y double prime of t would be s squared y of s minus the value of the function at 0 minus the value of the derivative at 0. I'll move my big dumb head out of the way in a second. Cool. So when I start this initial value problem, and in general you're just going to, when you see this, run through, hit it with a Laplace operator, Laplace transform operator, like that. Okay? Here's y double prime. Laplace transform of that is s squared y of s minus s times y of 0. So minus s times 2. Minus 2s. Minus 12. And then the Laplace transform of negative 2 y prime, so minus 2 times, Laplace transform of y prime is sy of s minus y of 0. Y of 0 is again 2. So we have minus 2. And then we have plus 5y. What's the Laplace transform of 5y? What do we call it? What's the Laplace transform of y? Little y. What's the Laplace transform of little y?
Y.
Big y. What are you going to say?
Oh, never mind. You're replacing them with the other equation.
So this is the Laplace transform. Y double prime. This is negative 2 Laplace transform of y prime. This is plus 5 times the Laplace transform of y. We have to do the other hand, the right hand side as well. Let's put this on your paper. Hopefully you have enough room. I clearly don't. So on the other side, oh, by the way, I'm going to stop and start my recording so I don't lose 17 minutes here. Okay. So on the left hand side, we're going to take we'll plot this guy here, that 4e to the negative t. Take its Laplace transform. It is 4 over s plus 1. Laplace transform of e to the negative t is 1 over s plus 1. So Laplace transform of 4e to the negative t would be 4 over s plus 1. All right, we can clean this up a lot, so I'm going to do that right now. In fact, here's what I'm going to do. I'm going to keep the terms that contain a y of s on the one side. Now, every term that doesn't contain a y of s, we'll move over. So we're going to end up with s squared y of s minus 2s y of s plus 5y of s equals, I have a 4 over s plus 1 already on the right-hand side, but I am also going to throw over, we have a minus 2s, he's going to go over. I have a minus 12, and this negative 2 times negative 2 becomes a plus 4. Negative 12 plus 4 is negative 8, so I'm going to throw the negative 8 over to the right-hand side, I get a plus 8. Okay. I'm going to do a couple things in this next step. I'm going to factor out y of s from this. By the way, look at the coefficients of s here. S squared minus 2s plus 5. We had y double prime minus 2y prime plus 5. This is not a coincidence. 1, negative 2, 5. 1, negative 2, 5. That's not a coincidence. That will always happen. If you get something different here than you did here, you fucked up somewhere. Okay? Equals. Now I'm going to get a common denominator with this. S plus 1 times 2s plus 8 would be 2s squared plus, now the 2s plus an 8s is 10s. We have 8 plus a 4 is 12. Cool? All over s plus 1. 2s squared plus 10s plus 12 all over s plus 1. Lastly, we're going to divide through by s squared minus 2s minus or plus 5 to give us y of s equals 2s squared plus 10s plus 12 all over s squared, which by the way, you know what? Yeah, that's true, whatever. S squared minus 2s plus 5 s plus 5 times s plus 1. Cool? I'm going to go over here now, erase this stuff. And say y of s equals 2s squared plus 10s plus 12 all over. This bottom piece does not factor. Sorry to ruin your day. S squared minus 2s minus or plus 5 doesn't factor. So we have to complete the square. It's going to give us s minus 1 squared. I'll move out of the way in a second. Plus 4 times s plus 1. That's how you complete the square with that s squared minus 2s plus 5 term. Shit, did I goof? Not really. So we're going to do partial fraction decomposition with this, but this is an irreducible quadratic. We saw that we couldn't factor this, so we're going to have as plus b over, I'm going to write it as s squared minus 2s plus 5 to start, but we remember that is s minus 1 squared plus 4 plus c over s plus 1. Remember, we can get the value of c for free, but the values of a and b cannot be gotten for free using the cover-up method. We're going to have to use a common multiple, least common multiple denominator or whatever, and solve the system of equations. So let's go ahead and quickly find the value of c though. What value of s causes that denominator to be 0? Do you have any questions, or are you good so far?
Yeah.
Negative 1. All right, plug in negative 1. Negative 1 squared is 1, times 2 is 2, minus 10 is negative 8, plus 12 is 4. So we get 4 on top. We're not plugging in here, we cover that up. Negative 1 minus 1 is negative 2, squared is 4, plus 4 is...
Wait, I have a question.
Yeah.
For the as plus b, why did you use the denominator that we had before?
Yeah, I told you, I said this earlier. Just because it's going to be easier when I get a common denominator. I probably shouldn't have completed the square just yet. That was a little premature of me. Anyway, plugging in negative 1 to our denominator here, not the s plus 1. Negative 1 minus 1 is negative 2, squared is 4, plus 4 is 8. So I get 4 over 8. So that's the value of c, 4 over 8, or 1/2. Okay, now that I've got that, sadly, cover method doesn't work anymore. So we're going to have to get a common denominator. This s plus 1 needs to go over here, so I have as squared plus bs plus as plus b plus, and then 1/2 times this is 1/2 s squared minus s plus 5/2. And it needs to equal my numerator of what? 2s squared plus 10s plus 12. Good. All right. Let's start by grouping the powers on s. So we have s here, or s squareds. How many s squareds do we have here?
1.
We have 1a. How many? 1a.
1a.
How many here?
1/2.
1/2. How many at the end?
2.
Equal. These equal 2. So it immediately tells us that a equals 3/2. That's nice. That's wonderful. Okay. What about our s terms? Actually, I'm going to skip the s terms because the s terms involve do whatever how you please. We now know the value of a is 3/2, but I don't like it. So I'm going to go straight to my constant term just because I'm like that. So what constant do we have? Not a constant, not a constant, not a constant. There's a constant, b. Any other constants? Plus 5/2 needs to equal what constant we have on the right? 12. So that tells us that b is equal to 12 is 24/2, so minus 5 gives me 19/2. Cool. So we have a, b, and c. Let's take it over here now. We want to find the Laplace inverse of. So y of t. So basically, here's the deal. This is y of s. And if we find the Laplace inverse of this, we'll find our solution to our differential equation. So we're going to find the Laplace inverse of this. Laplace inverse of 3 halves s plus 19 halves all over, now we'll complete the square, s minus 1 squared plus 4. Then we have a plus 3 halves, no, plus 1 half over s plus 1. Now, as far as this rightmost term goes, the 1 half over s plus 1, that ain't no thing. That's just the 1 half e to the negative t, right? When we pop that guy out. This is going to be a pain in the ass. So here's what we're going to do. What do we want this to be?
Cosine.
Right, we want to be a cosine.
And e to the
What do we want this to be? What do we want this numerator to be?
2. Oh wait, cosine s.
No, close. You're closer. It always needs to match this. We want this to be s minus 1. So the third thing we're going to do is, I guess, factor out of 3 halves. Okay, we'll factor into 3 halves. Let's split this up. Actually, you know what? I want to go ahead and take care of the 1 half over s plus 1. I know that immediately to be 1 half e to the negative t, right? That was painless, quick, and easy. That guy's done. We have to take care of this, though. So I'm going to factor out, this was the 3 halves here. I'm going to factor out of 3 halves. So watch carefully. So watch very carefully here. I'm factoring into 3 halves. Okay? That means I multiply everything on the inside by 2/3. What's 2/3 times 19 halves? 2's cancel. We'll then have a 3 on the bottom. If I factor out of 3 halves here, I'm multiplying the inside by 2/3. 2/3 times 3 halves is 1, so that gives me the s I want. 2/3 times 19 halves cancels the 2's and puts a 3 in the denominator of the 19. Now the question is, I want this to be an s minus 1, so I'm going to do this. I'm going to say minus 22 over 3 plus 22 over 3. Why that magic number 22 over 3? Because what happens, what's 19 over 3 minus 22 over 3? What's this going to give me? What's 19 minus 22?
It's 1.
It's not 1, but
3 over 3.
I want you to say the negative.
Okay,
19 minus 20, negative 1. That's what I want, right? I see the s minus 1 here. So, am I still recording? Okay, good. So I'm going to have 3 halves Laplace inverse of s minus 1 over s minus 1 squared plus 4. This is the s minus 1, right? So then I have left over a plus 22 over 3 over s minus 1 squared plus 4. What's the Laplace inverse in this guy? This is your desired what? Cosine with a shift of?
E to the 1.
Right, a shift of 1. E to the t, e to the 1t, and cosine of what?
2.
2t. 3 halves, e to the t, cosine 2t. How about this guy? Don't forget there's a 3 halves on both this term and that term. So whatever we get for this guy, we're going to multiply by 3 halves. This would be a what?
Sine.
A sine with a shift of how much?
A 1.
A 1. And it's a sine of what?
2t.
Sine of 2t. So we're going to go ahead and write e to the t sine of 2t. Now, the Laplace transform of sine of 2t would put a what up here?
2.
A 2. Well, what do we have up here?
A 22 over 3.
We can say that really was an 11/3, right? Because an extra factor of 2 that pops out from this would give us 22 over 3.
Times the 3 over
Times the 3 halves, we shouldn't forget about. What's 3 halves times 11 over 3?
11 over 2.
11 over 2. And that's our answer. We're going to stop the video for a moment and check Wolfram Alpha. Actually, we'll not stop the video, but I'm going to pull up Wolfram Alpha and see that this works. So you're just going to watch me type something in. So here's something really cool you can do. Oh, great. I got to use my guest UF internet. I haven't done that. 7907. Wolfram Alpha. Okay, here's what you can do. You can type in, this is for all you viewers at home as well. You can type in y double prime or y apostrophe minus 2y apostrophe plus 5y equals 4e caret negative t. And then you separate with commas. You would say comma y, open parentheses, 0, y, okay, let's use the black marker, comma, y of 0 equals 2, comma, y prime of 0 equals 12. And it will solve that thing straight up. Hopefully we did it right. Hopefully you don't get anything wrong. So y double prime minus 2y prime plus 5y equals, what was it? 4e to the t? E to the negative t. 4e to the negative t. Comma, y of 0 equals 2, comma, y prime of 0 equals 12. And hopefully we get this to pop out. Fingers crossed. Again, you are going to mess these up. I very well may have messed this up too. I've just gotten so proficient at it that my mistakes are limited to maybe 1 in every 20 problems. It's going to give me an answer. Really? It usually gives you an answer. I don't know if it's like thinking. Maybe if I type in the word solve. So I might have just lied to you about Wolfram Alpha doing what it used to do. There we go. Shit. We're close. We're very close. Oh no, we're right. Cool. I hate it when they do this. Okay. Their answer is the 1/2 e to the negative t. We already had that. They have 3/2 e to the t cosine 2t. We have that. Then they have 11 e to the t sine t cosine t. But they're using a double angle formula, right? They're using this, so don't.
They would be 1/2.
This would be 2 sine t cosine t.
Yeah.
But that 2 cancels the 11/2 to make 11. So again, be wary when you use Wolfram Alpha because sometimes they invoke some weird identities that you should know. But in case they do that, don't freak out. Cool? So we got it right. Good. No mistakes. Do you have any other questions? We can do more of them, but it's we've only been going for an hour and about hour and 20 minutes. I can talk about that weird one involving the ln.
Sure.
So what do they want you to find? The Laplace transform of?
Let me find it.
Is it the Laplace inverse they want you to find?
Piece.
Yeah, it's the Laplace inverse, I'm sure. Let's do
Yeah.
an example though first. What is the Laplace inverse of arctangent of S? I'm going to stop and start. Okay, so here's, I gotta try and figure this out. As always, it messes with my head. Oh, okay, got it. This is really hard. So there's some unknown function. The Laplace transform of f of t equals capital F of s. Right?
Yeah.
Some unknown function and some unknown Laplace transform. Oh, God. What do I have the answer in my head. I just can't lose my mind. How do I go about doing this? Okay, let's do this. The Laplace transform of t, f of t, would be what? What does the extra factor of t do? It means you need to do what to this? Remember that rule way back when? For every power of t that you have to do what to this f of s?
Shifting.
Mm-hmm. Take a derivative.
Oh, that's right.
And in fact, because it's one derivative, what do I have to put out here in front? Something else that's here. You take n derivatives and you multiply by -1 to the n for as many. You multiply by -1 as many times as you have powers of t, but you have, since only one t, you have a negative out front. Okay? Let us suppose for a minute that this is the f of s. This guy is f of s. Okay? What would f prime of s be? What is f? So f of s is arctangent of s. So what is f prime? What is capital F prime of S? On your notes. This is F of S is arctan of S. What is F prime of S? I'm asking you.
Is that the 1 over S minus? Is it?
Gotta know that one. So this is F prime of S. It's 1 over S squared equals 1. Now, does this look like a Laplace transform you know?
Yes.
Which one?
Sine.
Yes, sine, right? It is sine. Sine of what?
1t.
Sine of 1t, right? So this would be sine of 1t. Or rather, this is the Laplace transform of sine of t, right?
Mm-hmm.
But this matches this guy is associated with this. So this is t times f of t. Okay? So how do I get my hand? If t f of t, it really should be negative sine of. This is a negative here, so we'll throw in a negative later. But if t f of t is equal to sine of t, what's f of t?
Sine of t over t.
Sine of t over t. So that's this guy. Of course, we need to introduce what?
Negative.
A negative. So the Laplace. So here's the result. The Laplace transform of negative sine of t over t is arctangent of S. Or you could say the Laplace inverse of arctangent of S is negative sine t over t. This one was very hard, so I'm going to recap it because I was kind of all over the place. Here's what we're doing though. We're using that rule that involves an extra factor of t, means you differentiate your Laplace transform. So arctangent of S is not a Laplace transform we know. However, it just so happens that Laplace transform's arctangent of S's derivative looks like a Laplace transform that we know. Right? I'm going to recap this. I'm going to start in a more sensible fashion. Let's back this all up. So, Laplace inverse of arctan of S. For our purposes, we're going to call this f of S, and the Laplace inverse of this would be f of t. Laplace inverse of f of S is equal to f of t. What is f of t? This is our goal. We're trying to figure out what the hell this is. Okay, what is this f of t guy? Well, how do I figure that out? It's not any one of the Laplace transforms we know. But maybe we can use a trick that involves the derivative of arctangent of S, namely that rule that says if you're asked to take the Laplace transform of t times f of t, then it's negative f prime of S. Or in general, the Laplace transform of t to the n of f of t involves negative 1 to the n and n derivatives of f of S. Okay? Let's erase this stuff. So we're going to say maybe the derivative can help us. If we know the derivative matches a Laplace transform we know, we'll just set it equal to this guy and solve for f of t. So what's the derivative of arctangent of x? That would be
1 over s squared.
1 over s squared plus 1. Is this the Laplace inverse of anything you guys know? Yes, namely what?
Sine.
Sine. Right? Now, because this is f prime of s, this is also equal to the Laplace transform of t f of t. Now really, the Laplace transform of t f of t produces a what?
Negative.
So because there's not a negative here, there must be a negative here, right? So this guy matches this guy. Basically saying f prime of s is two different things. It's negative tf of t, and it's 1 over s squared, or the Laplace inverse of 1 over s squared. Yeah. This is a little confusing. I'll say this. Yeah. So f prime of s is equal to 1 over s squared plus 1. It's also equal to the Laplace transform of negative tf of t. But if I want to take That's right. This is not quite right. We'll just say the Laplace transform of sine of t. These are equal now. This thing in this bubble and this bubble are the same. So sine of t equals negative t f of t. Solve for f of t. Divide both sides by negative t, and you get f of t equals negative sine of t over t. Let's do another one. Let's do the one involving the ln's. So the other one involves... Oh, how's the video doing? Okay, it's still recording. I'm just going to make them up. Don't have to be the same logs. So this one wants us to find the Laplace inverse of something like ln of s plus 1 over s minus 2. Say s minus 3. Cool? Now the question is, same thing as before, we're going to call this f of t. Or f of f, capital F of s. And this will equal f of t, and our goal is to find that f of t. How could I find that? Well, we're going to start by looking at the derivative. The derivative might become simpler if I split this up, by the way. ln of s plus 1 over s minus 3 is the same thing as ln of s plus 1 minus ln of s minus 3, right? Okay. So now, what is the derivative of this? This is f of s. What's the derivative? What's f prime of s? 1 over s minus 1, or s plus 1, I should say, minus 1 over s minus 3. Right? F prime of s is, of course, equal to the Laplace transform of f of t, right? What am I missing? The Laplace transform of t f of t isn't quite f prime of s.
The negative.
Negative. There needs to be a negative here. You can say there's not a negative here, but there needs to be a negative here, but we're not going to deal with a negative here. We're going to put the negative on this guy. Okay? This guy is the Laplace transform of what? What functions? E to what power?
Negative 1.
E to the negative 1, so e to the negative t, right? Minus e to what power?
E to the 3t.
E to the 3t. But now, these guys are the same. So we set those equal. If I ask you to solve for f of t, what would you do?
Divide by t. Negative t.
Divide by negative t. So f of t equals e to the 3t over t minus e to the negative t over t. That's it. I wish there was another one like that. You ever like any other problems that are like that? I'm trying to
I
think.
think that's the only one he really did.
Yeah, arctangent is a good one. I'm trying to think of some other functions whose derivatives give you some sort of fraction like that. Square root doesn't do shit. I know I came up with one a long time ago. Well, I can't think of anything right now.
That's the only weird one he did.
Yeah, but then arctangent can crop up. This one can crop up. Oh well. If I think of any others, I'll show them or share them with you. But these are like, they're hard to find, because what you're looking for is a function whose derivative is a common Laplace transform that you know. Arctangent gives, oh, here we go, got it. I knew there was one. What's the Laplace inverse of ln s squared plus 1. This one's great. This one can't split up like the last one can. The ln of s plus 1 over s minus 3 you can't split up. So we have ln of s squared plus 1. And then again, we call this f of s, right? This is f of s. This is the Laplace inverse of f of t. What we're trying to find. We're trying to find f of t. Well, once again, we're screwed here. Nothing here is helpful to us. I don't know the Laplace. I don't know any function whose Laplace transform is ln of s squared plus 1. So maybe I take its derivative. What is the derivative of ln of s squared plus 1? Asking you.
2 over s squared plus 1.
Not quite. You're missing something. What's the derivative of the inside function?
2s.
And you said?
2s.
There you go. You need the s. I don't think you said s. Cool. So this is f of s. The derivative of f of s is as 2s over s squared plus 1. Do you recognize this as a... Oh, by the way, before we do anything, what is f prime of s in terms of the theory that we know? This is equal to the Laplace transform of what?
Negative t.
Negative t f of t, right? What is 2s over s squared plus 1 in terms of Laplace transforms that you know? It's the Laplace transform of what?
Cosine.
Close. Cosine of t. We're missing something.
2.
2, right? There's a 2 here that's not normally there for a cosine. So here we have, now we have a match. These are equal. Solve for f of t, what would you get? If this equals this, what would f of t?
Negative 2 cosine of t over t.
Negative 2 cosine of t over t. That is the Laplace transform, Laplace transform of this function is equal to ln of s squared plus 1. Crazy, right? So if you ever, again, here's the procedure. If you ever ask the Laplace inverse of something strange, something wacky, I'll stop and restart so I don't lose this part. If you ever ask something crazy, Laplace inverse of something wacky like this, and again, nothing that you know from your table of Laplace transforms, you go ahead and call that f of s. Then you examine its derivative because maybe that's going to be useful to you. So we said the derivative of ln of s squared plus 1 is 2s over s squared plus 1. Now before we talk about this 2s over s squared plus 1, we're going to remind ourselves that f prime of s is equal to what? What is f prime of s always equal to? It's equal to Laplace transform of negative t times the function that we desire to find, right? Laplace transform of negative t f of t. Then we say, okay, now we've kind of equated the theory. Let's go and examine what Laplace transform this is. This is the Laplace transform of what function? Well, we said it's got an s in the top, it's got an s squared plus 1 on the bottom. This is a cosine. There's an extra factor of 2, so this is 2 cosine t. But now that I have this and then the same, I just set these two circle those bubbles equal to each other. Negative t f of t equals 2 cosine t, and solve for f of t. And once I do that, I get negative 2 cosine t over t. And that's your Laplace transform, or Laplace inverse. Cool?
So you only do this when you don't have like any other way to solve it.
Right. If you don't know, if this doesn't look like, and certainly this one was not on your table. Arctangent of s is not on your table. Anything involving ln is not on your table. So you wouldn't be able to do this without this trick. Cool? That's all we've got. We can do another solving IVP. Let me see your notes, though, if there's anything interesting.
This is what he went over in last class, which is just basically, he went over
your table,
a lot of the table.
Mm-hmm.
He did one like this. He solved one of these, and then he did this one, which is basically what you
Systems
did.
of equations.
Yeah.
So you're doing systems of differential equations. Did you do this earlier in this class? Solving systems.
We did some
solving systems of differential equations?
Yeah, we did some with this stuff.
Let me see.
Like the variables and stuff before. Like how he solves the variation of parameters and stuff.
This isn't variation of parameters, though. This is systems of equations. This is that you have... Yeah, this is systems of equations. This is like chapter 5 stuff. And I don't know if you did chapter 5.
Yeah, I think we did.
Okay. I haven't seen it yet. Mind if I see? I'll stop the video. Don't need it anymore.